I think there might be a problem with the cable, but who knows. So in the meantime, we'll just do it the old style, and we'll just continue on. So the videos are now being uploaded. One video from Tuesday is already on the site, so you should be able to see it there. I'll put a link to it in the syllabus, the lecture, the appropriate lecture. You know, if you can't get enough of me here, you can wait and watch me online. I didn't realize how fast I talk. Like, I have no idea how you understand a word I say. It's a miracle that you understand anything I'm saying to you. So, even I can understand what I'm saying. So we also posted some notes about the project, and I'm imagining there might be a few questions. But the basic outline is you form groups of 2. You choose an interesting paper, where interesting is defined by me. So, which means that you get to choose a paper, write, I think, basically just take the paper, give a link to it. We, myself and the TAs, will decide whether this is an appropriate paper for you to work on. And if it's approved, then you get to work on it, which means what? Which means basically you, sounds kind of dumb, you write a 10-page report of paper. Well, if the paper's 10 pages, like, you just give the paper, that would be a 10-page report. Which is kind of like saying that, you know, since I have the lecture notes online, you don't need to come to the lecture. Wait, no, I didn't mean that. So, but what I want from you in this project report is not just a regurgitation of the paper. That doesn't give me any extra insight. What I want you to do is do a critical reading of the paper. And you know, critical reading is normally you think of in a humanities department, but we do it all the time in every field. Everywhere you read some piece of research, you're doing a critical reading, which means you're trying to understand what exactly the contribution is. Not what the authors state, not what they claim, but what it really is. And that requires not just believing what the authors have to say about the paper, but understanding the context in which a particular paper exists. No paper exists by itself, no matter how awesome the authors will claim the paper to be. There is a past that led up to that paper, and there's a future that leads beyond that paper. And the only way to understand an actual piece of work, no matter how great the conference or whatever, is to understand it in that context. Why did things get to that point? What was the intellectual development that led to that work? Why is that work important to you or to anyone else? Why is people citing? What has been the impact of that work? This kind of historical understanding and critical understanding of the work, not in terms of time history, but in terms of intellectual history of the work, is what I'm hoping to see when you read this paper. Which means to do that, you need to have insight. You need to be able to read the paper. You need to be able to understand at a basic level what's going on. But you also need to understand at a somewhat deeper level what's really going on. How this paper solves maybe a bottleneck that other papers were unable to break. How it opens up new ground by framing the problem in a certain way. And so on and so forth. Now, of course, these papers are from the cutting edge of the area. So you're going to be reading the papers that are probably well beyond what you've ever seen before. So it is going to be completely normal to read this paper over and over again and have no clue what they're saying. I mean, you can understand the words, they're all in English, but it makes no sense. That's very normal. A paper is not a story or something you can read linearly. You will often read a bit here, read a bit there, jump back and forth, go here, go there, and it takes a while. So I guess what I'm trying to say is, this is one of those things where more time actually helps you. So you read it again, read it over again, argue with your partner, just go back and forth, have some idea of what's going on and realize the idea is completely wrong. And then do it again. You need time for this. So the deadline for submitting the proposal is, I believe, the 19th, 2 Fridays from tomorrow. We will hope to get feedback to you very soon after that. And then you can start working on it. But you will need the time you have, the 2 months odd, to sort of really engage the material. Otherwise, you will write a report. It'll be a regurgitation. You'll get an average grade, and that will just be an average. Or worse, depending on how well you do. And if you want in order to get a good score or a high score, that's what I'll be looking at. Okay. So that's what the project is going to be about. So take a look at the description. There are two posts up. One for what you need to do to submit, and one is what the report will be expected to be. In other words, what the project is going to be about. So hopefully, if you have any questions, again, post them on the forum, and we can answer, hopefully clarify all your concerns there. Okay? So that's the first sort of job you have to do, sort of start forming your groups and then think of your project. You will submit your proposals independently, just for administrative reasons, and then we will put you in a group, and then when you get graded, you'll get graded. I think you can work together, but you will submit individual reports just to get a sense of how much is group effort, how much is yes.
So are we being put on teams or assigned teams?
No. You assign yourselves. Yes.
Okay, some clarification. So you can both turn in the exact same report if you work together, or that's not what you mean?
I'm not sure what that means.
Okay.
So let me give me another date. Since you want to submit the project in December, this is hopefully not something I'll spend a day on and think about and post an update tonight or tomorrow about that. But for the submission, you submit them in. And just mention there's a format. You submit to say which project partner is going to be. You have a link. It's all detailed there. And so then we'll in Canvas we can administratively put you into groups, and so that we can do that. We do all the stuff that we need to. Yes.
So the proposal needs to be submitted separately, or
Yes. The proposal for the project needs to be submitted in. Yeah.
so we take two people and both submit the same proposal.
Yeah. But your group partner name will be different, so we'll just match you up there.
Okay.
And then we'll create the administrative. Yeah.
Redundancy in the.
It also would be funny if two people submitted different things. That would be awesome. That's a bit. Good. Yes.
You said it needs to be theoretical and not experimental.
Yes.
So theoretical and not such. I mean, how is theoretical different from experimental? I mean,
They're not exactly the same way right now. How is theoretical different? What I mean is this. This is an algorithms class. We are studying how to abstract problems, how to think about them conceptually, how to reason formally, mathematically, about the correctness and the efficiency of these methods. There are many tools that have been developed over the years, over the past 40, 50 years of this field, to do these things in extremely sophisticated ways. The paper you pick will be on one such thing. A paper that takes some interesting idea and implements it is a good paper. It's a very interesting paper. It's not an algorithms paper. Right? It's a paper in a field that, for example, you might look at a paper. People might pick up a paper in networking that sort of takes some routing algorithm and implements, and it looks at all the different parameters involved and optimizes it very carefully. Does a lot of very good engineering. That's a great paper, but it's not what this class is about. That would be great for networking, not for this class. Right. So what I want to focus on is papers that explore some deep concept in the way we think about computation, in the way we think about algorithm design, in the tools we have to do algorithm design well. Right. What you're seeing in class are the basic tools. Right. These are things that have been around for 30, 40 years. What you'll see in these papers is the cutting edge stuff that's going on right now. There's of course a wide gap, which is why it's going to be hard. And you can make that gap a little bit easier by choosing a paper that's somewhat older. But these papers will be intrinsically about coming up with new ideas, new things that in 20 years will be in an algorithms class. That kind of thing. Right? Yes?
Where do we find these kinds of papers?
I mentioned 4 conferences, and this is again, if most of your grad students, this is something that's probably good practice to have. How do you go find papers? There are 4 conferences listed. These are called, in short, Fox Talk, Soda, and Sausage. We are hungry people in our field. So, but these are the Foundations of Computer Science and the Symposium on Theory of Computer Science are the 2 major conferences. Soda is a conference on algorithms, which is it's a bit more accessible in some sense.
You have some things listed.
Sorry?
You have some things listed.
I have those names listed. So, Google is your friend. And then you can always just email me if you have any, or rather, post a discussion forum if you have any question. It'll be easy to find stuff. If you have, any of you heard of DBLP? DBLP? Yeah, one person. So DBLP, if you Google it, is sort of a resource in Germany, which it's a very good indexing service for all the papers and all the conferences that you might not think about. So they have all the papers nicely cataloged. They even have links to electronic editions where they have them. So the paper might be published in this venue, but DBLP has a record, and if you click on the record, it'll go there. It has the BibTeX entry for it, and so on and so forth. So that's a good resource. So one resource is DBLP. Another resource is the ACM Digital Library, which again for at least 3 of the 4 conferences I mentioned, they will be indexed on the ACM Digital Library. Google again will find it. So this again is something that is good to learn how to do. And again, as mentioned in the report, in the suggestions, the best way is probably not to go and start reading titles. You'll just get drowned in information. You'll probably understand 1 word out of 3 in the titles because they're very cryptic and they use a lot of jargon. The best way, I think, is to start off with things that you find interesting, topics that you think are interesting, and then start from there and start looking. And again, once you have a partner, you'll have someone else to brainstorm with, and hopefully you'll make things a little easier. Okay. So the drop deadline is over. People who are in this class are actually officially in this class. If at this point there are no more slots available, I've emailed all the people on the wait list, so those they're probably not here, but if they were, I apologize. So those of you who managed to make it, good for you. So I'm glad you're in. And so now that you can't drop the class, I can bring all the heavy machinery, all the hard stuff. Okay, let us continue. We were talking about dynamic programming last time. We looked at a simple example of recursion, where the recursive formulation does not directly lead to an efficient algorithm. One of the things that we liked about divide and conquer was all you had to do was think about the recursion, and the algorithm kind of wrote itself. You just do it recursively. But we saw with the calculation of the Fibonacci sequence that this doesn't quite work. That even though a recursive formulation is what you want to think about, that's not how you want to implement it. Because the implementation, if you do it naively, would be exponential or worse. And that's precisely because the set of sub-problems you care about, to keep track of, are not that many, but you're trying to compute them over and over and over again. And some kind of clever bookkeeping allows you to avoid that problem. And so we got this idea of think top-down, implement bottom-up. I talked about as a way of thinking about how dynamic programming works. Okay. You can also think of it as a kind of divide and conquer where you don't know how to divide. We'll get to that in a little bit. So let me take another example of a problem, and again, this is all from the notes, so hopefully you've seen some of this already, where we will try to think about how to come up with a solution that's recursive, and then slowly walk our way into a dynamic programming solutions problem. And the problem is going to be what is called the increasing subsequence problem. And the input to this problem, so we'll call it LIS for short, longest increasing subsequence. And the input to this problem is a sequence. So I have a bunch of numbers. So I'm going to write out a bunch of numbers here. I have a simple example here. Let's say I have 1, 4, 3, 6, 3, okay, let's say 5, 6, 2. This is my input sequence. It's of length 7. Okay, so the input set is length 7. So n equals 7. Okay. My goal is to find a subsequence, which means a sequence, things are in order, but it's picked off from this, but may not be consecutive. That's what typically is called a substring. A subsequence that is always increasing. So for example, the subsequence 1 and 2 is an increasing subsequence. 1. But I want the longest subsequence. Okay. And what would the longest subsequence here be? 1. Okay, so 1, 3, 5, 6, 8. This is a length 5. And while I can't force you to believe that this is the longest, by inspection, at least in this case, you can check. You can tell that there isn't anything that's bigger. Yeah. Okay. So the LIS of this, if we call it sequence S, once again, if we call this sequence S, the LIS of S is equal to 5. Yes.
Are you just because you could also do 4 instead of 3?
Good question. In this particular version, I'm interested in just the length. But if I wanted the actual sequence itself, I could produce either way I want. And then any answer that is as long as the maximum length will be acceptable. I want to have a particular preference for it. That's right. So you could do 1, 4, 5, 6, 8 or 1, 3, 5, 6, 8. These are both the same length. Either of them will be acceptable as a number. Right now, I just want to find the number. Problem clear? Okay. I want a recursive solution to this problem. I claim recursion is God's gift to the human race. Let's come up with a recursive answer. Recursion is so awesome. Let's do it. How do I come up with a recursive solution to this problem? And of course, the first thing I know in recursion is divide and conquer. That's my tool. Right? So, let me try to do a divide. So, what would be the most obvious divide and conquer strategy for this problem? Any thoughts?
To move one element and check it for the others.
Sorry, repeat.
You can probably remove the last element and find the longest subsequence of the remaining strings, and then you can check the longer one and see if it's variable.
Okay, so what you're saying is that in order to solve the problem recursively, I'm going to solve the problem recursively on a set of length 1 less, and then see if I can add the last element in. That's kind of what you're saying. Alright, so this is a perfectly decent recursive strategy. So I might say, okay, I'll look at the optimal solution for this, and then see if I can add this in. Of course, to do that, I need to not just maintain the size of the solution, I need the actual solution itself. Otherwise, I wanted to check if I can add the last one. Right? But that's okay. So, so if I do this recursively, so the recursive algorithm will say something like LIS, let's say 1 through n, A1 through n, would be something like compute LIS 1 through n minus 1. And for now, we'll assume that we're getting not just a number, but the actual sequence, some actual sequence. And then check if an can be added. In other words, if it's greater than the last element of the list, and output either, if yes, then set output LIS 1n minus 1 concatenated with an, else just output. Okay, well, let's say with s equal to this, or just output s. Right? Okay. It's not going to be too hard to check what the running time of this method will be. Can you see the recursion in your head? The recurrence equation? What's it look like? Just so you should be able to see it now. Okay, so I have t of n, I have t of n minus 1, and I have some kind of constant time operation. So we have n squared and 2 raised 2 to the n. But this is the recurrence.
Can you move that?
But lambda is here.
Yeah.
We move the bad ones. Anyone?
And
It's n.
But the algorithm is a little bit wrong, right? The way you're doing it.
So is it n squared, is it 2 to the n? Which one is it? Anyone would, so I could do proof by intimidation, says, are you sure it's n? Or I could do proof by democracy, says, well, does anyone not believe it's n? Or I could say, well, the answer is it's n because at every step I throw in 1 and I reduce by 1. Throw in 1 more, reduce by 1. So you can't again solve the Lamarck's theorem. Yet another recurrence you cannot solve the Lamarck's theorem, but you can unroll it. And if you just guess t of n is equal to exactly n, then yes, n is equal to n minus 1 plus 1. Okay. But as seems to be the case, we may have a little bit of a problem. As you put it so nicely, it's a little bit wrong. Tell me why it's a little bit wrong.
Every time the recurrence rate, we think about n minus 2, it depends on the else case is wrong in a way because of s. We might have to go in and check in, and there might be one more recurrence which is longer than.
You're saying that this will not give you the optimal solution?
I don't think this is giving the solution at all.
But then you should be able to produce an example where it fails.
4 and 8
guys.
4 and 8 are swapped.
These two? So you're claiming, okay, if I understand you correctly, you're saying if we take this input, swap 4 and 8, it will break this algorithm. Is that what you're saying? Okay, can we check that? So the claim is that the sequence, I'm going to write this here, 1, 8, 3, 5, 6, 2, 4 will fail to give the correct answer with this algorithm. Wait, no it won't, or no, his counterexample is wrong? Someone said no. I don't know what that no meant. Okay, you can check this. Just run it. I'll give you a minute. Run it. Let's see what happens.
The answer is
So tell me what answer. So what is the right answer? The right answer is 5. 5. The answer is 5. 4. 1, 3, 5, 6. The answer is 4. Either 1, 3, 5, 6 or 1. That's it. 1, 3, 5, 6 is the only answer. So this algorithm better not give you an answer of 4 if it's going to be wrong. So can anyone know?
the answer is 2.
The answer is 2.
Yeah, if we follow that, it's 1.
Yeah, I was gonna say the answer is 2.
Answer is 2. You're also saying the answer is 2?
I want to understand, like, this algorithm is not actually giving the longest sequence to ith index.
Pardon me? It's not giving?
The actual longest increasing subsequence till ith index. So, for example, we are computing on the previous result
Yeah.
and checking with the last option whether it belongs to the subsequence by this constant time equation.
Yeah.
But this LIS1 and minus 1 will not give you the longest subsequence till n minus 1.
Why not?
Because
Isn't it recursive? If I believe that, I'm trying to argue by the inductive hypothesis that this would work, right?
we are not comparing with every other element. We are comparing only with the last element here. So,
But if it's increasing, I'll need to look at the last one, right?
let's say there are two subsequent, like for example, 183.
Yeah.
Let's say the
Okay, how about we look at we'll get back to the point. There was another question. There was, yeah, yes?
This algorithm will work only if we fix the starting point. Like we want to start the longest subsequence from the first element, I guess.
Do we?
There is no constraint like that.
There's no constraint like that, correct.
So in this algorithm will work only if we are finding a subsequence starting with the first element.
Okay, but then in this input, it is actually starting with the first sequence. So it should work, yes.
Well, I mean, there's no guarantee that the longest subsequence of your subproblem is going to be within the longest sequence.
Okay, that's a very good thought. I want you to hold that thought for about 1 minute while I work through this example. But hold that thought. So we compute the LIS of this, and we check if we can add 4 or not. Okay. Well, to compute the LIS of this, we compute the LIS of this, and check if we can add 2. So since this is a 4, this is like what's called a head recursion. Just keep going back. So in the beginning, we start off with 1, right? We can add 8 to it. So we add 8 to it. And then we're stuck. The recursion will fail all the way back. So you'll end up with 1, 8. Right? So this algorithm doesn't work. This is a new thought. Usually we had a divide and conquer, it just kind of worked. This doesn't work. And this doesn't work. I think I've had a minute for what you said. Can you say it again?
Well, yeah, I mean, it's sort of what you're saying.
No, please.
Okay, well, I mean, you can't guarantee that, 1 and 8 is going to be, because it's the LIS of those two, it's not going to be in the LIS of,
Right.
the whole set.
The problem here is that we are making the assumption that even if this was computed correctly, that this check to the last element will in fact give us the optimal solution for the whole problem. We don't have an argument that this is true, and in fact we have now an argument that this is false. We have a counterexample. So our recursion has failed. It has failed us. Now what do we do? You could imagine applying a divide and conquer strategy, which is even more clever. Remember, I'm wanting more clever things, right? So you could say, well, I want to split down the middle and do something with that. But in fact, see, that was what I was first going to do. But in fact, the example is better because you might start worrying, you're worrying too much about running time at this point. You're saying, oh, I want to split down the middle to keep balance. But the same issue that comes up there comes up here, namely, just because I compute the optimal solution on this set, and even if I do the optimal solution on this set, there is no reason to believe that trying to combine them will give you the right answer. It may be you need something that's really bad here, and something that's really bad here, but together they work to give you the whole answer. Right? So, what do? We want to use recursion, but somehow this is not working for us precisely because we can't make this argument. Yes?
Would it make sense to do the brute force solution first and see how bad that is or see what that entails?
Sure. What would a brute force solution look like?
Like start with the first one and find the LIS, including the first one. Go through every single possible combination, which is going to be crazy hard.
Crazy hard.
But and then save that away and then start with the second one and try every single combination.
Aha! I do believe you have described exactly the second algorithm I was going to do for this problem.
Okay.
What the hell? We'll do it that way first. So, take that thought. The idea is to do this brute force. And this is a good way to think about this, actually. And the idea is, let us take the longest increasing subsequence starting at 1 and see how good that is. Take the longest increasing subsequence starting at 2 and see how good that is. That's not that bad because how many possible sequences am I going to look at? There are only n of them, right? That's not so bad. I can live with n. It's not exponential. It's not, constant, right? That's okay. So but how did I find the longest decreasing subsequence starting at 1?
Well, okay, it's going to require some kind of recursion to.
So how do you do it?
Try to balance.
So what would if I said I want to find the longest decreasing subsequence starting at 1, which is different to saying I want to find the longest decreasing subsequence. This goes back to what you were saying, we have to somehow fix this, that fixing this is what's important. How would I find, yes?
What if you start at the other end?
Oh, you're changing the algorithm. Hold that thought, we'll continue with this, but unless you think this will not work at all. Do you think this is not a good way to do it?
No, I just think it'd be easier to start at the other end. It just seems like, because at the other end, you don't have, at least the first part, you have just one element. Like, okay, that's.
So how would you formulate the question? Find the longest decreasing subsequence ending at something? Is that how you want to say it?
Yeah.
So find the LIS that ends at a particular point. Okay, let's hold that thought. Maybe we will try it that way as well. Let's try this way first and we'll try it that way and we'll see which way it looks easier. So if we want to find the LIS starting at 1, can we express this recursively in terms of another form of LIS starting at somewhere else? Starting at 2, right? Someone has to play the role of this, right? So how do we say this? So we want the LIS of A1 through N starting at 1, right? In order to solve this, what I'd like to say is that somehow recursively I compute the LIS of 2 through N starting at 2, or the LIS starting at 2. And then what do I do with that? So let's say I have the LIS, so let me rewrite this notation just to say, okay, let's say LIS I is equal to the length of best sequence starting at I. Okay, and going all the way to the end. So can I express LIS I in terms of something that comes later? Can I express it in terms of I plus 1 or I plus 2? I have to think recursively now. So the trick is here. One trick here is the following. Suppose you're all powerful and you know where the next element will be. Suppose you know for sure that the next element in the longest increasing subsequence starting at I is actually at J, which is after I. Then what do you do? Then how will you write this out? So what I told you that. So if I knew that the sequence has to next go to J, but I don't know what happens after that, I could write LISI is equal to 1 plus LISJ. Right? If I knew J. But I don't know J.
You can try every J.
Try every J. One of them has to work.
Try the max of them or something like that.
But there's one more condition you need, of course. You can't just pick any J. Some J's won't work at all. AJ has to be greater than AI because you want it to be a longest increasing subsequence. I think is that what you're saying? Yeah. So such that AJ is greater than AI. We don't yet have an algorithm. I want to emphasize this. But we do have a recursive formulation. We don't even know if it's correct yet, but we have something. So you see the rationale here? The rationale is that first of all I said, okay, instead of trying to formulate this in terms of the LIS in general, let me constrain my set and say I want to find the LIS starting at I. By the way, how would I get the actual answer to this from this kind of solution? I would look for the LIS starting at N or 1. Or 0, at minus infinity in some sense. That will allow me to sort of jump ahead. So I put a sentinel at minus infinity, which is lower than everything. And then I'd say, find the LIS starting at 0. So that will allow me to go from minus infinity to whichever the right start point is. So it doesn't have to be 1. I can't say the LIS starting at 1 because that constrains me to, in fact, pick 1. because I'm doing 1 plus. Okay. So I know I can recover the solution to the original problem from this recursion. Now the question is, well, 2 questions. Is it correct? And if it's correct, what is wrong? So if I had to implement this, well, okay, let's talk about the correctness. How do I know this is correct? So again, for any recursive algorithm, correctness comes from induction. In here, we had an inductive hypothesis that this was in fact the best solution from 1 to n minus 1. What we were unable to conclude was in fact that the optimal solution from 1 through n came by forming these 2 possibilities. Now here, what are we saying? We're saying that suppose we in fact have the best solution here for all j more than I. So we induct in the length of the sequence. These are all sequences of length less than I through n. So the inductive hypothesis, yes, in fact we find the right LIS for each of them. Can we conclude now that we have the right LIS for I? And the answer is yes, for the following reason. Imagine the optimal solution. This is kind of a weird thing to do because you don't know what it is. But imagine the optimal solution that starts at I. Right? It has to pick something after I for the next element. Right? You're finding the optimal solution starting at that element by the inductive hypothesis. So opt can do no better than pick that, in fact, one and add this to it. Because if there was a better solution starting at j, the optimal solution would have picked that one, and you would have found it too by the inductive hypothesis. So it's very circular, right? This is how this recursive reasoning goes. You're assuming that the algorithm is in fact correct for shorter sequences. And that allows you to conclude it must be correct for this long sequence. And the subtle change from the previous one is that A, we parameterize this recursion to make it easier to understand. And that allowed us to actually argue about why this should be. Yes?
So are you assuming that you have the optimal solution for the whole n or only for the I?
I assume that by the inductive hypothesis, if I compute LIS j for j strictly more than I, that it is in fact the optimal longest increasing subsequence starting at j. By j to n. From j to n. By the inductive hypothesis. That's what the inductive hypothesis is telling us, right?
But ith element is not in the sequence.
No.
Ith element is not in the sequence.
Not yet. Well, not yet. Because remember, we are asking for what is the optimal LIS that starts at I. We're not asking for the optimal LIS.
Oh, that's fine. Okay.
Because remember, every sequence starts with something. Or it's empty, in which case we have a sentence for that as well. So since every sequence starts with something, that's the insight that allows us to say, oh, okay, let's try to find the optimal sequence starting with 1, with 2, with 3, with 4, with 5. Something should be. So this is the brute force aspect of this. You're doing recursion, but you're not relying on a clever divide strategy to make sure everything works. You're just going to say, I don't know, I'll try them all. So it's recursion combined with a guess for the divide step in some sense. So it's like a dividing contour where you don't know where to divide. So I'll try all possible ways of dividing. Okay. So what's the runtime? Why?
Because we are comparing one element with every other element. So
you're comparing one element with every. You mean when you do this maximization?
Yeah, maximization. Yeah.
So in other words, to solve it for I, you have to look at n minus I cases,
yeah,
and so on. So n minus I, n minus 1 plus n minus 2 plus n minus 3. How much space do you need? What is the information you have to store in a table?
And
why? All you need to store is LIS of j for all j. So you need a table to do that. And how does this table fill up? It actually fills up backwards. Right? It goes backwards. From right to left. Because the ones that are further up are the ones that are going to give you information about the ones back. So there's this kind of flow, if you think of this as a table, there's this kind of flow of information going backwards like this. Okay. Let's return to the other point. So, Trudy, so
Well, that's what I did.
that's what you're trying to do?
Yeah.
But you could also form this by saying LIS J is the best sequence ending in J. I thought that's maybe what you had in mind.
Well, I was just saying that you should basically fill the table that way.
That's what you're trying to say. Fill the tail backwards. Okay. Okay.
And that you should store it in the first one.
Right. And so then, okay. So then you get exactly this. There are other ways to formulate this recursion. And the thing with dynamic programming is that there isn't an obvious way to formulate the recursion. The obvious way gets you in trouble. There isn't even one unique way to do this. There are different ways that will give you slightly different answers that might all be correct. So sometimes with dynamic programming, you need some recursion, you get one answer, but you might get a better answer if you're a little bit more clever. So another way of thinking about this, for example, would be, which is going to sound a little strange now, because this is clearly the resolution. But you could say something like this. Suppose you kind of wanted to go forward. Right? So, what we'll formulate is a different strategy. And again, what you can do is an exercise to see how you can get correct dynamic programs without them very different from each other. Another way to state the recursion, the recursive state that we're working with, is to say, I have the value that I've seen so far as the highest element of the sequence I've built up already. So we'll call that, the top, or previous, I think it means the notes. So let me just use previous, but that's what's my notes. Okay. And I have the sequence I'm trying to evaluate now. So let's say it's from A, J through N. Okay? And the semantics of this thing is that find me the best LIS, right? That must start above the value previous, because that's what my previous state was, and then continues on. Okay? So the best sequence that's at least so high in the value, starting at J. So you may not actually pick AJ. So if I had this as my recursive state, how would I describe this? How would I compute this recursively? What might I try to do? So one thing you could do is say, well, let's suppose that AJ is more than the previous value. Okay? Suppose this is true. Then what could you say? So if this is true, then it might be possible to include AJ and then continue on. So for example, then you could say our LIS, you would just compute the LIS of AJ and then a J plus 1 to N. Right? Which again is the right pattern. So it is recursive and it's a smaller size recursion because this length is small. This could work, right? Or you might decide not to pick AJ, whether or not it's more than previous. So you could also, let's say this is 1 value. This is, let's say, S1. You could also compute S2, which is the LIS of previous and AJ plus 1. Right? And again, you would do this because you either picked AJ or not to be in your set. You don't know. So you're going to try both possibilities. Okay? And then take the maximum. Okay? Whichever one's better for you. This is a very different recursive formulation. And again, you can argue that this will be correct by induction. Because in your optimal solution, either you pick AJ or you don't. And I'm trying both possibilities. And take the one that's better. I'm not saying that for sure I'll pick it or not. I'm just trying both and see what happens. I'm looking down the road saying, okay, if I pick this, what happens at the end? Let me look at the end of the book and see what the story says. If I pick this way, what happens at the end? And then pick the one I can do the best answer. It'd be nice if life could do that as well. Of course, this suggests a much more horrible recursive algorithm. Because I'm calling two subtasks of size n minus 1. And if you have a recursion that calls two subtasks of 1 less the size, what kind of runtime are we looking at? I'm hearing exponential. I'm not hearing everyone say exponential. Think in your head, t of n is equal to 2 times t of n minus 1. That sounds like a tower of Hanoi. Okay, it's exponential. That's how we solve recursion. Just kind of sniff it. It smells exponential. So that would be terrible. But again, we know that with these kinds of problems, the naive recursive strategy is not a good idea. But this also tells us something else. How many different distinct sub-problems are we going to get? Obviously, there are only n values for this, right? There are only suffixes of the array. So there are n different ways you can describe this. How many different things can you put in here? Notice that every element that shows up here is some element of the array. Because in the next level, I'm going to call AJ on this, and that happened previously as well. So there are n choices for what could go here. A1, A2, A3, A4. There are n choices for what could go here. Okay? So if you made a gigantic matrix, saying, okay, this corresponds to the value of previous, so it will be A1 up to AN, and this corresponds to the suffix that I'm dealing with right now. So again, it's indexed by A1 and 1 up to N. This element here, with J and I, will contain the value LIS AI A J to N. Right? And if I want to solve this value, right, I need to look at this value, which is the value right here. And I also need to look at this value, which will be what? It'll be some value up there. Because let's say I is less than j, so the actual j value is going to be up here, and you go up here. So these two values are going to control what you see, what the final answer is. So again, in this matrix, if you start filling from the top down, whenever you reach this, you make sure that you already have all these other values filled up. And you can just keep walking your way down. So it's just like your Fibonacci sequence, it's just like that one. That's a lot more efficient. Because now you have n squared space, and you're going to spend a lot more time doing this. And again, you could say, why should I care? I have a better solution there. The point is that there are different ways to formulate the recursive strategy. They have different number of parameters, which controls the running time. And they have different formulations that may change the way you think about parameters. So, all right, let's take a 2-minute break. Or we want to. Answer here where all numbers are above this. This is like so it's like I got to this threshold somehow from previous work. Now I want to continue on, but I can only continue on if all my numbers are more than this level. So I have to, it's like my memory. It's like I'm saying, okay, I got up to this point in my sequence. I don't know what happened before, but I know I'm this high right now. I better pick something else. So I have, that information has to go into my solution. Otherwise I might pick something that's really random. Okay, let's continue. So I argued, so far I've argued that there are certain ways to recognize that something might be recursive but might need a dynamic programming solution. By the way, this isn't notes, but I thought it's worth pointing out for posterity since you're video, is that the whole phrase dynamic programming is the legend has it that Richard Bellman, who invented this, named it this sort of very weird name, frankly, as basically as a marketing pitch. There was some funding agency, I think it was DARPA or somewhere, that hated computers and computer science and do them. So he needed a name that was somehow catch their eye. So he thought it has to be dynamic. Dynamic things are good. So it's like it's programming, but it's dynamic. So that was the name of this thing. So if you're wondering why it's called dynamic programming, there's no good reason for it. It's a marketing thing. The thing with dynamic programming, I hate this along with DPs, is that the way we recognize them is that there is first of all recursion, and that's fine. But what makes them different from a divide and conquer strategy is that there doesn't seem to be an easy way to know how to split things up. There seems to be a way to do it, but it's not obvious. It's hard to find the right dividing point. You maybe don't know the dividing point, or it's very going to be a lot of work to do it. There just seems to be something that's not quite right about this. But when you do the recursive formulation, you see that even though it looks like it's going to be, expensive, or you have to do a lot of recursion, the number of problems you really need to consider is very small, as I argue. Right? So in all these cases, the number of subproblems is small. It's linear, or it's quadratic, it's subpolynomial. But the recursion seems to take exponential time. And that points to an inefficiency in how you're thinking about the problem. That while you're thinking about it recursively, you should implement it bottom up. Solve your subproblems and bubble them up to the top to get your answer. So that says dynamic programming is a very clever way of doing recursion. You think recursively, but you implement it bottom up. But what if the number of subproblems is itself exponential? Then it would seem like it's hopeless, that you shouldn't be able to apply a dynamic programming strategy because the number of subproblems I would look at is exponential. So I'm not going to get any benefit from going bottom up versus top down. The subtle point here, and this next example is going to show this, is that it doesn't matter how many subproblems you have. What matters is how many optimal subproblems you have. In other words, if in a lot of dynamic programming, you're trying to optimize something. You say, I want to find the best of this, the smallest of that, the largest of that. In that case, the set of solutions that could be largest or smallest or best is often much smaller than the total number of possible solutions. So it's not that the total number of solutions is small, they're big, but the number of interesting solutions is small. So this is another twist of the whole dynamic programming story. And you have to be able to recognize that. Because that's when you could apply dynamic programming. It doesn't always work, but it's sometimes. So let's look at an example. So the problem we're going to look at is what is called curve fit. So in this problem, I have a bunch of points. So let's say I have a bunch of points like this, right? I have some data, I collect some data, and I want to fit a trend line to it. Now if you look at data like this, so there's some kind of line of best fit I can fit this. So you compute some line of best fit. And if you know basic calculus, you'll realize that I can write out a cost function that says, what is the distance from this point to this best fit line? The line has two parameters, its slope, and its y-intercept. Right? So y is equal to mx plus c, which is how I was trained to learn these things. I think there's a big geographical sort of divide among us. If you come from India, then you write stuff like this, and if you come from England, you write it a slightly different way. So I don't know how you all think about how do non-Indians think about how do you write an equation of line? Is it like ax plus by equal to c or so? Sorry? That's what you do? Okay.
Y equals mx plus b.
B. That actually was one of the choices there. In that article, that was one of the subtle differences there. Yeah. So anyway, so you have two parameters. Whatever they are, there are two parameters that describe your line. You can write on a cost function that says, okay, if my line had these two parameters, what is the error from each of the data points which I actually have? And you can do some calculus and find the optimal solution. This is standard basic statistics 101. How to find the line of regression. I will not go into the details of it. Okay? So once you do that, you can find a line of best fit. But suppose my data actually looked like this. Now, of course, you might say, well, you need a curve. But let's say I want to do lines, because lines are easy to work with. They're linear, they're piecewise linear. One line is going to be not that great. But 2 lines might be awesome. Maybe there's some kind of phase shift happening. It's like, okay, fine, I'll look for 2 lines. There are 4 parameters, I can write my calculus, I can do some stuff. It's like, oh wait, suppose my data looks like this. Now even 2 lines are not going to work very well for you. You need 3 lines. It's like, oh, that's fine, 3 lines, 6 parameters, I can do this, it's great. And you see what the story's worth. The general problem of curve fitting, at least in this particular flavor of it, there are many flavors, says, I have a bunch of data points and I want to fit a collection of straight lines to it. Now if I stop there, then the answer is clear. Here's my straight line that fits the data, great. I think we have some statisticians in the audience who are going to laugh at me now, because this is like a classic case of overfitting. Overfitting means you're really fitting your data too carefully, which is wrong, because the data itself is noisy, and you shouldn't take it that seriously. So then what do I do? You're telling me I can't use 3 lines or 4 lines, you're telling me I can't use n lines. What is a poor data analyst supposed to do? And the answer is, if you take a machine learning class, you'll learn about things like regularization and nonsense and things like that. The basic point here is that you somehow have to control the amount of pieces you use. Call it Occam's razor. And for now, since I don't want to get into all the hundreds of different ways you can do this, let's just say that I have to pay $1 for every line I use. So I get better error, but I pay more. Okay? So if I use, suppose I use lines, L1 up to LK to fit the data. Then for each piece of line segments, let's call them line segments because they're going to be each with a certain range. So then for each line segment, I can calculate the cost of using the line segment to approximate the data. There'll be some error term there. You basically take each point, measure its distance, and add all those distances. There's some cost function. So we'll call that C of L. Call that error of L, actually. So the cost I'm going to pay of L1 to LK is going to be equal to the sum of all the errors for the individual lines, okay, whatever the error happens to be, plus some constant times k. So I'm paying for each extra line that I use. So that's one sort of poor man's way of trying to limit the number of lines I use. I can use more to get better error, but now I pay more. So it's a trade-off. Okay. Given a collection of points in the plane, find me the best set of lines, where best is defined as minimizes this corner. This is my problem. I'm not going to tell you how many lines there are, there will have to. I just pay more if I use. Does the problem make sense? Is it well defined? Happy with the problem definition? Is there a recursive dynamic programming strategy for solving this problem? And so first of all, I want to point out one thing, that if you think of each line segment as being sort of controlling a certain collection of points, right? So those are the points that are being approximated by a line. Then the number of ways of partitioning this is very large. Right? If I have k pieces, it's a number of partitions of n into k things in order. And that's a very large number, it's definitely exponential. So the number of sub-problems I have to look at here is exponential. This is what I was saying. So you would not be blamed for thinking this is not, doesn't seem like a problem that is amenable to a dynamic programming solution. But in fact it is. And in order to design the solution, we need to think recursively. And one of the best ways to think recursively about things online is, as indicated, try to go backwards. Imagine the optimal solution. Okay. And let's say the optimal solution, for arguments, let's say our solutions are required, just to make it simpler, to start at the first point and end at the last point. And they can do what they want in the middle, but they must start. Okay. So if we imagine what the optimal solution is doing, it's doing a bunch of stuff. This is my last point here. Right? And in fact, let us further assume, again for ease of argument, that every line segment is between 2 points of the input. In general, you might not want to do this, but in this case, again, to make the dynamic programming reasoning easier, let's assume that every line segment must be between 2 points of the data, just to keep things discrete. So, if my optimal solution ends at the last point, right, it goes somewhere. We don't know where, but it goes somewhere. It goes all the way across to some point before. So let's call this N, and let's call this G. Okay? And then it goes and does something else. Like I'm not saying anything surprising here. The optimal solution has to go somewhere. Might go all the way to the beginning, that's fine too. Can I use this as a basis for a recursive formulation of this problem? So in other words, the best cost solution for n points can be written as the best cost solution for some other smaller set of points plus something plus something. What can I do? Just with this observation. So again, the way we think about this is, okay, what must the optimal solution do? I have no idea, but it ends at the end, it has to go somewhere. And at that point we call it G. Now what do you see? Remember our trick, we won't know what J is, we're going to try and guess it, right? But that comes later. But let's say we knew G. How would we express the cost of this in terms of some other costs, recursively? Yes?
Can we actually say that the best fit line actually includes the last point?
I'm saying that for now. By fiat, I'm saying that this is part of the problem definition.
We're pretending for now.
Yeah.
Okay.
There are things you can do. I don't want to, it clouds the discussion a bit more. It's still a dynamic program, but it gets messy.
So it's at least the cost of the line, the best solution of J, right? Can we at least say that?
Sorry, repeat.
Can we at least say it's the cost of the solution at J?
What is the solution at J mean? The solution till J, the solution from J, what are we talking
Till
about?
J, I would say.
Till J.
And if we're going for it.
Yeah, okay. So you're saying that if you write down the optimal cost, it consists of some cost here that we're paying somehow, plus a cost here. The claim is that, more importantly, that the cost here is in fact the optimal cost till J. So I can say that the optimal cost of 1 through n can be written as the cost, let's call this the error of going from J to n, and we don't know what this is yet, we'll fill this in, plus 1, or plus D, for the actual segment that we paid for, plus, and this is the critical step, the optimal cost from 1 to J. This is a very important claim.
What is DAV?
D is the cost from the amount of money you pay for 1 second. Because I said D times K is the cost.
Okay, plus D. Okay.
D is this constant. So why is this true? Remember how we're saying this. The optimal solution ends at n and goes somewhere. If the solution it had before was not optimal till J, well, I could replace it by the optimal solution till J. It would not affect anything that happens after that, because it's fixed at J. In other words, in the dynamic program, we don't need to know what's going on here, we just need to know what's optimal. And then we can add this onto it. In other words, the best solution here has to involve the best solution up to this point, and then move. This is what is called the optimal substructure property. That is the thing that creates a dynamic program. You have to have something like this. Otherwise, you cannot reason, like we saw in our original recursion. You cannot reason about how they're going to combine. And this works because I broke it up this way. If I was trying to say this forward, so the optimal solution starts at 1 and goes somewhere. Actually, you could make this work that way for the optimal solution.
Yeah,
In that case, it works as well. Yeah. But for some problems, as we saw in other cases, it's not quite symmetric. You have to find a way to say that what happens before does not affect what happens afterwards. And on the line, any kind of problem on sequences, this is what usually happens. That if you think about before and after, you can separate the two parts out. It's not a dividing formula. I don't know what J is. But if I knew J, then I can separate it. So once I have this, what is this? This is the error I pay for a single segment that connects J and N. But by calculus, as I mentioned earlier, I didn't say exactly what it is, but it's a simple calculus to figure out, okay, if I have a line that starts at J, ends at N, and there's no calculus in fact, I just calculate it. I know what the line looks like, I just look at all the costs and I can write it down. It's a simple expression. Right? And then I have to compute this. Of course, since I don't know what J is, I rewrite this as really the min over all J less than N, error of J comma N plus D plus opt 1 to J. Again, same pattern. Think of what the optimum might do, assume you know what it's going to do next, then admit, okay, I don't really know what's going to do next, I'll just guess. Yes?
So is J one of the points that are given?
Yes.
What
Because
is it?
as I said, I require that the answer always have as its endpoints the segment one of the input.
What if there is another point in between X and J? Higher or lower? That is
Between
two.
N and J there's another point.
Yeah. Which is not.
But how did I define J? I said J is the next point that opt picks. So opt decided not to pick anything. I'm just trying to do what the optimal solution is doing. I don't know what it's doing, but I'm trying to do what it's doing. Right. So does that answer your question?
Yeah.
So this is a very frightening looking reference because you solve so many different subproblems. But that's where the next step comes. You look at this and say, okay, how many subproblems are there? How many different kinds of subproblems are there? Well, of course, I need to compute opt 1 through J for all J. So there are n of those. But I also need all these numbers. These can be computed easily, right? For any pair of points, I can compute the cost of the line that goes through them and how much it approximates the errors of the lines that are the points along the way from J to N. So this is just a number. But then how many numbers are there? There are n squared of these numbers. Because for every pair, I have to do this.
No, but point to line, right? Error of J to N is.
Error of J to N is the error involved in taking a line segment that connects the jth point to the nth point and adding up errors of all the points in between.
Yeah, that should be the n, right? That should be n minus J.
No. There are two endpoints.
There are J and N are the n points.
Okay, but look, what about the next level of recursion?
Or next level of
It's going to be error I through J, right? Some other parameter
Some
K
other-
through J.
Okay.
So in principle, I have to look at all possible pairs.
Because I want to find many values. Okay.
Exactly.
Yeah.
So I need to look at all pairs. So let's make a table. I need to store opt 1 through J for all J. I need to compute, and this can be computed ahead of time, error I through J for all pairs I and J.
Yes.
Okay? So there are n squared numbers here, there are n numbers there. There was a question? I hear some hesitation. Is there a question? No? Okay. So, okay, I have these numbers, but what does my algorithm look like? What is the, so, you know, setting up the recursion is only one part of the plan. The next plan is actually design the algorithm. What does it look like? What do I do? So the first thing I'll tell you, just compute all these numbers ahead of time. Because that's easy. Then what?
Sorry, it's not clear. Is it I comma J or J comma N?
Sorry, I comma J for all I and J. I and J for all I and J.
Oh, okay. That I have already understand.
So I can do them all. That's it for the matrix. So how do I run the algorithm? Nitin?
So you just start from some point at the beginning and then
So first of all, am I going forward or am I going backwards?
forward, anyways.
Well, the recursion is going backwards. So I probably need to go forwards. Because in order to compute this number, I need to know this number. So I'm computing the opt i's from the beginning, going forward. Okay, so go on.
Yeah, so just begin with begin going forward and keep computing one by one. Right.
Right, so you compute opt 1.
Yeah.
That's just 1. That's 0. Then you compute opt 1 comma 2. Right? Which is basically, you know, you take a line segment connecting them. Then you compute opt 1, 2, 3, which you just apply this expression. So opt 1 to 3 will be basically the min over all j less than n over j equal to 1 and 2. So if you have 1, so I first compute opt 1, which is just this. Opt 1, 2 is just these 2 points. Now if I have 3 points, right, my solution could be this, it could be this, it could also be this. I don't know yet which one is going to be. I just figured out the min over all these things.
You actually do the min of all the 3 solutions.
All the 3 solutions, because I'm in the min over, well, there are 2 solutions, right, min over j. Yeah. I mean, technically, yes, there are 3 because the one choice is to go all the way to the base. So you just go, yeah. Then if you want opt 1 through 4, you do the same thing all over. Because now you have opt 1, 2, and 3, so you know what's going to happen. And then so on, so on, so forth. You fill out formulas. So again, this is a problem where the number of solutions is exponential. That's the number of partitions into whatever number of pieces. But the optimal substructure that you have found is very small. Because the optimal solution only is going to do things a certain way. All the other solutions are not going to be optimal, I don't care about. I have to build up optimal solutions to build up optimal higher solutions. This is the optimal substructure. So this is I think these are the 2 things that make dynamic programming probably a confusing paradigm. In that it's one of the first examples I think in algorithms where you think one way but you design a different way. Normally we think, we design, we implement, we think in code and we write our code, it's all just written out. Here you have to think one way and implement it a very different way. And that I think is what, at least I think, I don't know, you can tell me, that's what causes a bit of confusion about how to design that. Because you have to think kind of non-linearly about the problem. Coming from a different angle. And this only gets worse. I mean, it'll get better for 2 lectures and get worse. One second, yes.
Is optimal 1j or
yeah.
between ij. It's only one dimension.
Well, 1 through j, not ij. 1 through j.
I'm saying in this question we are mentioning error j to n and d plus optimal I to j.
Actually, no. I said optimal 1 through n is in terms of optimal 1 through j. That's actually important. That's why it becomes one-dimensional. So my table of opt values is just a single array. But I have this ancillary information which of n squared size that I have to keep around. So you're right that I fill up the table one at a time, but it takes me a lot of work to fill up this table. Because I will look up all the, I have to first compute those values ahead of time, then I will look them up when I get to. So the right time is going to be at least n squared. You can, if you're not clever about this, it'll take you n cubed. But if you're a little bit more clever, you can use an n squared time. And this will take n squared to fill up because you're taking linear amount of time at every step to fill the next n cubed. But there are only space-wise, it's this plus that. Is that was that question? Yes.
So if I'm comparing j and j plus 1,
yeah,
then I throw away j.
You're comparing j and j plus 1. What does that mean?
Sorry, if when I'm trying to do opt of 1 comma j, and then when I'm coming from the other side, when I'm computing.
Yes.
So I do 1j, and then I want to do 1j plus 1.
Right, so that's 1j plus 1 here. Let's say here, you want to compute this.
Yes.
So you look at this expression. You look at all numbers less than your j plus 1. Right? So in other words, okay, so let me do this here. Okay, this is good, this is good. So what does the algorithm actually look like? I think is the point. Yeah. It's kind of weird, right? So let's say at some point I have filled out opt 1 through j, as you said, right? So I have my table here, and I have filled them up to j. Now I want to fill in j plus 1. Yeah. Okay? Okay, good. So now I have my points. I have my first j points, and I have the j plus 1 point here somewhere. Yes. So I'm going to say, look at the min over all numbers less than, this is confusing now because I use j. Maybe I should use, let's say I fill up 1 through k, and I want k plus 1. So I look at all numbers j less than k plus 1. Okay? Right?
Yeah.
So I say, okay, maybe what the optimal algorithm did was to go back to some number here, connect it up optimally here, which is opt 1 through r, let's say, and then draw a straight line all the way to j plus 1.
Yes.
Which corresponds to one of these entries.
Okay.
It corresponds to the entry where this is exactly that. The straight line, pay for the straight line, and look at the table for the rest of it.
Yes.
Do this for all values.
Okay. So at every point I'm actually going back.
Yes, you're going back all the way. That's why it's in square. Yes. And you have to because you don't know which one.
I don't know.
If I had a divide and conquer strategy, I wouldn't be doing this. I would know where to cut.
Yeah.
So this is like a lazy divide and conquer. I don't really know where to cut, so I just try everything.
Okay.
And that's another way to think about how to design these things. Does that make sense? This is a good question. So this is exactly how the algorithm works. It just keeps using this thing here to compute. But because it's already computed the previous ones, they've been stored in my table. It's not recursion, it's just a lookup. I just wrote. Any questions? Yes.
So we're basically saying that once we've computed the most optimal line or path, whatever, up to a certain point, we just need to figure out how do we find the next most optimal step.
Step. Yes. Very good.
And so the big question is, what's our base case? How do we find that very first optimal step?
What is opta 1 in this case? 0. You don't draw a line at all. Like,
Well, then what's opta?
huh?
What's opta, like,
2.
1, 2?
It's a straight line connected to them. 0 cost. I pay 1 unit and 0 cost.
So since we don't know where to cut, we are doing it sequence.
We're guessing, we're trying all possible cuts.
So why don't we just do brute force in that?
We are brute forcing. This is a brute force operation. We're essentially guessing all possible answers and taking the best of them. This is exactly brute force. So one of the things with direct programs is that practice will help. And when I put out the list of questions to work on, just practicing them will be very useful to sort of see the different ways in which you. After a while, again, you'll start, especially with problems involving sequences, you'll say, okay, there has to be a dynamic programming solution. Not always, but most times there will be one. Problem involving sort of pairs of things, there's probably a dynamic program hidden there somewhere. So you'll learn how to pick up these signs of the problem when it's applicable. It won't always be applicable. Yes.
So about the space that the algorithm requires,
Yes.
we don't know for when we have one call J, we don't know where J is. So
Yes.
for every J bit, we need to store the optimal solution.
And we are. We're storing opt 1 through J for all J.
So how much?
That's linear space. But that's not the problem here. That's easy. That's linear space. The problem is all these error terms you have to store. They're fixed. You don't have to store them in principle, right? You could always compute them on the fly when you need to. So then you're trading off time versus space. So if you don't have a lot of space, don't store them. Just compute them when you need them. Or you store them all up front and send squared space. So it's up to you. You just pay more time or more space. But the optimal solutions you store only linearly many. Because the optimal substructure is only one. If the optimal substructure, like in one other example, was I, j, then you need a whole matrix of solutions. All right. Okay. See you all next week.